All right. Afternoon, folks. Start recording. Cool. Recording there, recording here, recording in your brains, best of all. How are we doing today? Enjoy the holiday break? I'm glad. Makes one of us. No, that was fine. Lots of sicknesses in the air. I'm not sure if people saw. You all look very well, though, I can tell. Spot a virus. No, I can't. I can't lie to you. So, all right, so a little update on the courses. The Canvas page is now, I want to say full hard launch, but like mostly like hard-boiled launched. Like it's all like, so the landing page is up, and you can see there are links to the videos of every lecture that we've had so far. I'm about to put up the lecture notes from every one of those lectures, okay? I record them on my iPad as PDFs and put them up there. The first homework should be dropping soon, as should be your first quiz. I will be giving at least 2 weeks to do the homework. The first homework will be about using gradient descent in Python to solve some, in order to create a machine learning model for something a little more complicated than we did in class on Thursday. So, little note on class on Thursday. Thank you all for coming to the Python lecture. We do take attendance during the Python lecture. We do that through Zoom, and this is just so people know. I mean, I know some people like to join maybe over YouTube. Just make sure that if you're going to join through some other way, make sure you just log in to Zoom under your username or whatever you use, right? So we can at least see if you're there. Okay. No worries if you didn't do it the first time you watched over YouTube, but that way we can log attendance. All right. So today, I want to give people a little bit more information about, yes, question. It'd be nice if something we're pretty, so here's the thing. If you've got a weird username, sorry, a lovely username that is unrecognizable as your name, just put your name in the chat to help us out, okay? We're pretty good at deciphering, initials, inferring the year of birth from your class year. I don't know. We shouldn't be doing that stuff. But anyway, but it would be helpful if you put it in the chat. Okay. We'll examine the attendance records, and if people aren't showing up, we'll say, hey, just did we miss your username? Do we miss you? If not, just come to the lecture. Okay. All right. For the Zoom lectures, and also you are here today. Next week we'll start passing around an attendance sheet. So just pass around, sign your name. That's what we'll do starting next week. Okay, but I see you're all here, so why am I telling you? You're here. So we want to keep barreling forward with this machine learning course, and you're going to see that on the Canvas page there is a schedule for the term. We are building that out as we have more firm idea as to what topics can be covered on which lecture day. It's a bit fluid as we move forward. It's the first time we do this class, but we're also assigning some assigned readings out of the Goodfellow textbook. You can see some of the chapters there. We're starting to have chapter headings. You can see all that course schedule with then the videos popping up on that same table so you can click on them and watch them. Okay. All right. So keep an eye on that stuff. But today, I want to give you a little bit more background on machine learning more generally. I know we're getting a lot of that, but we're also getting some specifics. We're actually coding things, some real things. Okay. But I want to give you a little bit of a broader perspective because soon I'm going to want you to start thinking about your project groups and your projects. Okay? And it's helpful to know a little bit about what you are looking to do, based upon the course material. You need a little more information to determine what you want to do. So that's what we're going to talk about today. So all right, where am I? But today, 2026 is the 20th of January. Okay? So we're going to start by talking about trying to hit two things today. All right? We're going to try to hit paradigms of machine learning. That's the big one. This is going to frame how you think about your course projects, which you get to decide. Okay? Then we're going to see if we can talk a little bit about linear regression again, just to give you this little bit of teaser of linear algebra that I keep saying I'm going to give you, okay, about how to fit all of these polynomial curves, okay? But primarily, I want to see if we can talk about methods of differentiation. Okay? Now, there are all kinds of different tasks that you can solve with a machine learning method to create a model that then solves your task. Okay? So you can sort of see these as paradigms, but there's some broad categories. Okay? You think of them as paradigms or types of machine learning. Okay. Now there are, as with any sort of categorization, there's an arguable definitions to all these sorts of things. But to give you an operational definition, we'll talk about the main categories and a few sort of niche sub-combined categories. Okay. But what most people will agree on are there are at least two categories of machine learning. Okay. One is called supervised machine learning, or supervised methods. And the other one's going to be unsupervised methods. We'll get to that in a second. Okay. And the supervised, I always find that's the easiest to wrap your head around. Okay. And what all of these different paradigms have is a different relationship with the type of data that they have and how they use that data. Okay. And the tasks that they're trying to accomplish from learning from that data. Okay. So for supervised methods, use labeled pairs of data to predict future data. Okay? That's the broad definition. So labeled pairs of data. The key is this is labeled, okay? This labeled pairs of data. Classic example are something like classification. So this pad is yellow. Okay? This is an object, I have labeled it yellow. This jacket, I have labeled it brown. Okay? This is the data that I'm using. They are examples that I would give the algorithm, presumably to look at an object and then predict what color it is. That if I give it enough examples, it'll be able to predict color. This phone has a white case. The phone case is white. Okay? So there's paired data, meaning on one element, it's the phone, and then it's paired with a label white. Okay? That's what we mean by paired data. So we would classify, for instance, this phone case as white. So our classification algorithm is just good at saying what color a thing is. Okay? Classic example is, does this image have a cat in it? You give it an image. Does it have a cat? No. No is the label. Here's another image. Does it have a cat? Yes. The label is yes. Give it a new image. Yes or no on the cat. I'm sure I already told you about the dog blueberry muffin conundrum, right? Good. That sticks in people's heads. Okay. All right. So classification. So you would pair data. You could pair data with a discrete label. Cat or not a cat? Question. What the shape of what is? Okay, objects. So what methods do computers use to identify objects in general? Okay, and it would be a supervised method. Okay, and you give it mostly a lot of times an image, and then you would give it a label. So you had to give it a bunch of examples. And there's all these existing data sets that people put together, a bunch of images. This has a tractor. This has a dog, okay? Then it has to learn, right? Well, how does it learn? Well, the learning process, guess what, friends? We were coding it up on Thursday. Largely, it's gradient descent. So you know how we were trying to find the value of, what was it, m or something? We were trying to find some value that gets to the bottom of that curve, right? We started with a guess. We have a parameter that defines the model, okay? And then that guess wasn't very good, right? Then we follow the gradient down to a lower and lower cost. Go hit the bottom. So, and maybe the example I'll give next is a little bit more clear, okay? But the model is defined by those parameters, okay? So in goes a number, sorry, in goes model parameters into this model. You put in data. If it's an image, it would be a bunch of pixel values, okay? So you're looking at a screen right there, right? So each one of those things, each one of these pixels has a value from 0 to 255, okay? RGB. If red and green and blue are all on, it's white. So you have those little black dots. Those are 0, 0, 0. Those are all black, okay? So you would have all these pixels all in a row, and they have a bunch of numbers associated with them, okay? See, maybe if we're really good today, let's see if we have time. We'll do an example. Sometimes I do this in class. We'll improv. I think this is important because you're getting at a question which is like, we're starting with all these abstract data points on plots, right? And we want to tie it to something real, like an image classifier, okay? Now, to actually build a good image classifier, we have to go at least a few weeks later into the course, use things called convolutional neural networks, but we're not there yet. Excuse me. Little stuffy nose, it's allergies. So, another example, it's a great question. I know I answered about 20% of it. Thank you for your patience. What was your name? Natalie. Thank you, Natalie. Regression. Okay? Again, it's paired data. You have inputs. It's like your X. And then your output, which is Y, which is a number. It's not a discrete label like yes or no. It's a number, right? So regression, we have our data, our input data, X, paired with Y. That's our pairs. Paired data, X and Y. Now, my friends, I will also point out that X doesn't have to be just one number. It could be a whole vector of numbers. And Y could theoretically be a whole vector of numbers too. It's still paired, an input X with an output Y. And if you were doing a regression, maybe it does something like that. Okay. And this is the model we've been covering last few lectures. This is the thing that predicts that if we have some input X, what is Y? Okay? And the learning is when we come up with the parameters for this curve, which was iterative, right? That's what gradient descent was. We started with a bad guess, and it's making a slightly better guess. Okay? We'll continue with that coding lecture on Thursday. Okay? But I wanted to give you a big picture. So if you are doing your project, you're coming up with something that you wanted to do, what is your data? Does your data have labels? Okay? Or doesn't it have labels? Okay? Because if you don't have labels on your data, it very well may be an unsupervised methods. Okay? Unsupervised methods attempt to find structure in unlabeled data. Do a little dropping rate. We're getting some drop here. Audio is clear. We'll post the VOD afterwards and make sure it's a little higher rate. Yeah, the YouTube's not being cooperative today. So, all right. Unsupervised method attempt to find structure in unlabeled data. Unlabeled data. What is unlabeled data? Well, for instance, let's say you're on Amazon, buying things online, okay? It's important to Amazon to know that when you buy a soccer ball, you might also want to buy shin guards, okay? Because at which point they will say, have you considered buying shin guards? And that means they're more likely to click on it and buy that too, right? Okay. Now, what they're really often trying to figure out is what kind of customer are you? Like, oh, you are a soccer player. But you don't at any point provide them with direct information and labels saying, hello, I am Christian. I'm not a soccer player. I'm a bad example. Is there a soccer player here who wants to? Okay, soccer player. All right. So you are on Amazon. At no point when you sign up to Amazon, you say, hello, I am a soccer player. You don't provide them with that label, right? The data that you give them is the things you click on, the things you buy, okay? And so, but they would still love to know that you're a soccer player because that means there's all these things that they might want to advertise to you, okay? So what that might look like in Amazon's data, okay? I'm going to draw a plot, and let's just say there's data point x1 and x2. Neither of these are labels of, is he a soccer player? These are just points in space indicating things that he has bought. Okay, I'm making assumptions about your buying habits. They don't need to be real. These are all hypothetical, okay? All right, so when you are buying products, you might buy products all over here, okay? Maybe one of your teammates is buying products from the soccer team over here, okay? I am not a soccer player, so I am buying things that allow me to sit around my house over here and not exercise, okay? And I'm sure I'm the only person on the planet who does that, but let's assume there are other humans who also sit on the couch, and they're buying things over here as well. At no point did I advertise myself as a couch sitter, okay? But if I look at these data points, like here's things like gigando bags of chips. And here are things like shin guards, okay? Now, I, as a reasoning being, saw two clusters, right? Okay? I see the pattern. I see the structure in the unlabeled data. So if someone else comes in and starts buying things like here, oh, Amazon can then say, you're a couch sitter. I'm going to advertise super bags of potato chips. Okay? Right? So this is called, where I do this, called clustering. Right? That's an example of an unsupervised method. Yes? Maybe, so right now I'm drawing this two-dimensional space. Maybe it looks like, oh, actually, you're over, I'm just going to draw it with a temporary label here with green. You're over here, what is that, right? Now I might not be able to determine. Maybe that classification is too simple, okay? I'm trying to get the class to the point where we're going to do a very simple classifier where we just draw a line between, linear classifier, we just sort of draw a line between two sets of points, right? But right now we're assuming that this is only a two-dimensional axis. There's no reason it needs to be. Maybe there's a third dimension, whoop, coming out of the board. And so maybe it's a third cluster that looks like it's in between right here, but actually it's its own distinct cluster up there, right? And the thing about machine learning algorithms, they're really good at looking at these higher dimensional spaces. Things that like we could see in 2D, those clear clusters, right? To an algorithm, the number of dimensions is just more numbers in a vector. That's all it is to them. It's just math, okay? So it might come up with a third category of person. I don't know, romantic comedy binger. I don't know. Maybe that overlaps a lot with my couch setting. I'm not sure. I'm improvising here, okay? But so so coming up with so clustering would say, okay, here's a thing right here, or maybe try to assign a probability. The probability that you're in this cluster might be something that it does. But the point is the data labeled? No, right? I never had to label myself as a couch sitter until this very minute. Okay, that's what unsupervised methods do. So if you are coming up with a project, you might ask yourself, am I trying to predict labeled data, or do I not have labels on my data? I just want to look for structure. Okay, there are uses for all kinds of cases. Okay, so Natalie, your image recognition, identifying the image, is most likely a supervised method because it was provided with images and labels as part of a training data set. They used gradient descent to learn all the little W's in the decision vector. Voila, you have an image classifier. Now, most people would agree unsupervised and supervised are two very clear categories. Yes, question. It could be either, but the description I'm talking about with clustering is mostly, these are now two categories, this one and that one, okay? There's a classic example of something called a support vector machine, which machine learning people love their fancy phrases for things. Really what it's doing is it's saying, can I draw a line that makes sure that that I can separate two things? Actually, that's classifier. I'm sorry, I'm mixing things up. I apologize. I shouldn't go off script. But it will, generally speaking, these are two clusters. It'll say, here's a cluster here, here's the center of a cluster here, something like k-means clustering. Sorry. Apologies to people who caught that mistake. But it'll say, oh, no. But it'll say, here's the center of a cluster here, here's the center of a cluster here. What it'll try to do. Yeah. It can be probabilities as well. Question. That's a great question. This is where things get complicated. Saying, what if you like, how hard do you draw that line? That depends. You have some control over the algorithm, okay? What you're describing though is like, what if I give someone and I sort of test them, see if I can predict, I can get them to click on that, right? Okay, and you're trying to, and I see your quick question in the back there, Cricket. And I'm going to try to see, did I get it right or not with them? And then they'll tell me yes or no by clicking or not clicking, right? That's a different category of machine learning, a different paradigm that we'll get to in a second, called reinforcement learning, where you give me a yes or a no. Did that thing that I did, was that good? If yes, okay, then I'll change all of my machine learning model in this way. No, it was bad? Okay, then I'll change it in this way. Okay. It's a little fundamentally different. We'll get that in just a second. Does that give you a little bit more context? Thank you very much, Christian. Yes, in the back. Yes. So the question is, if computers are so good at seeing in high dimensions, and we can't, how do we know they're doing a good job? Is that the gist of it? Well, that is a tough thing, but we have methods, okay? Such as we talked about having a training set and a test set in some of our other things. So, but that's again for for supervised learning methods. For unsupervised methods, how do you know? Well, that's a tricky one. Well, maybe what you do is you change some of those hyperparameters of your algorithm. If you change them a little bit, does it change your answer a lot? If it is, then you might have some finicky data, okay? But there is a whole like art and science to knowing if you did a good job with your machine learning algorithm. But sometimes the answer is, I don't know if I did it the best I could. And that's some of the challenge with machine learning, because you're learning on concrete examples, and you're testing it with a handful of examples. You're not testing it on every example, right? So it becomes a lot trickier to know if you got it right. So the question is, what are the consequences of getting it wrong? If the consequences of getting it wrong are, oh, I thought that they were a soccer player, so I gave them a shin guard on their limited ad space, and they didn't click on it. It's like, maybe on average I lost out on a penny, of my business. To me, that's not catastrophic. Maybe to a business it is. But if you're using it for diagnosing a disease, for instance, trying to categorize patients, and you're trying to do treatments on that, that's a higher stakes thing, right? Sorry, this is getting a little more philosophical than I'm sure you asked for, Cricket, but hope we give you a little more context. The big question that you asked. Anything else before we move on to reinforcement learning? This is my personal favorite, reinforcement learning. We're still dropping, but still get audio. Okay, good. That's all right. So finally, so clustering is an example. So now we're going to go on to reinforcement learning. A lot of times called RL. Finds a model that maximizes a reward signal by interacting with the environment. Okay. Reinforcement learning. This is the most similar to optimal control, which many of you are in my optimal control class, just for context. All right? So you're trying to maximize a reward signal that comes from the environment. I just gave you all an example, okay? For instance, some people use ChatGPT for completely ethical purposes, we assume, okay? And sometimes when you type in a prompt to this large language model, so you basically type in text, it spits text back out at you, okay? We won't talk about how that works. That's a very complicated process, okay? Is how that works. We will talk about the category, the general category that it sort of exists in, but it's a very complicated thing. But at the end, it'll sometimes say, did I do a good job or do I not do a good job? Thumbs up, thumbs down, okay? And you may not click on it. You might click yes, you might click thumbs down. That's a signal that you're giving back to an algorithm as to say, was that good? Was that not good? Good is a positive reward. Bad is a negative reward, okay? Now, a much more concrete example, so it's really good for trying to come up with controllers for physical systems, okay? Where, for instance, for a robot, it's really, really hot in robot control right now to do reinforcement learning, okay? Where you say, here is my model, okay? And the model takes in the current position of the robot and spits out something for the robot to do, okay? Then we will create a computer simulation of the robot. We will spit in, we will take in its current position, spit out what to do, and then we will tell it, did it do a good job, did it do a bad job? If it's a walking robot, did it walk forward? If so, how far? Okay? Further is a good reward, higher number. Did it fall down? That'd be a negative reward. We'd say, hey, we don't want it to use a lot of power, so every little bit of power it uses, that's a negative reward. That's bad, right? Then it tries that model, sees how it does, we tell it the reward. And it tries a whole bunch of other options, okay? And we tell it for all of them, good, bad, ugly, all those things. Yes? Yeah. They're very, very similar things. You're talking about how in control, you're often trying to minimize costs, and in reinforcement learning, you're trying to maximize reward. Well, if you just said that reward is equal to minus cost, you're done. That's it. That's simple. You don't often get that many simple answers from me. Got one today, right? So if you're taking a course in optimization, you often talk about wanting to minimize a cost. That's just by convention. We call it minimizing cost. It's more cool to say, oh, I'm maximizing reward. So another example of not even an algorithm, but like if you're training a dog, right? Trying to train your dog to do tricks. What do you do if they do the trick right? Give them a treat, a reward, right? It knows to do more of that thing, right? So we just now do it in computers with much more with algorithms and neural networks and computer simulations of robot dogs, literally robot dogs. We'll do it with, and we'll give it virtual treats in the form of a reward function. Okay. My student Jacob, who's wait, he's there. I'm just going to point at you as a man who exists, who works with deep reinforcement learning. He's got a literal robot dog in the lab down the hall. He has to design a reward function. You know, how good is it to, is it walking straight? Is it turning when we ask it to turn? And he'll run it on a computer where he'll do, how many simulations do you do on a time? You doing 1,000, 2,000, or 4,000? 8,000. Oh, sorry. I'm out of it. 8,000. We're getting fancy now. We'll run 8,000 simulations of this robot, get a whole bunch of reward signals, and then it'll try to improve it. How does it try to improve it? Well, it has to have a derivative of the reward and wants to improve it, more or less, okay? So we'll talk about derivatives in a minute. I see 2 questions. First, you. It is not through Isaac Gym, but it's something very similar to Isaac Gym. Functionally, you could say yes, but literally, I have to say no. He's using a framework called JAX to differentiate what's a simulation called Mujoko. So it's a different simulation framework. We happen to like it for a research-related reason, but Isaac Gym is exactly an example of that. So a question over here. So you would have a guess. So the question is, like, do you have to define all the different models? In a way, yes, but you are going to try the same model on all those different scenarios and say, how is it good in all those different scenarios? That's an example for, robot control. Okay. So, and then once it's done, it'll try that. It'll say, okay, how well did it do? In what way should we move the model in order to make it better? Guess what method we use to figure out which way we want to make it better? Gradient descent. Technically stochastic gradient descent. Do you have any particular solvers? And is it just straight SGD, or is there what kind of solver do you use for your PPO stuff? Just SG. Yeah. Okay. But it's nothing. It's not like Atom or anything like that. It's that's the optimized. Okay. Yeah. Okay. The Atom. So you can. But SGD is the broader category. So we've talked about gradient descent. We'll soon be talking about stochastic gradient descent. Anyone know what stochastic means? Random. There's more randomness to how it works. We'll get to exactly how a bit later, okay? Because right now, the code that we ran on Thursday, there's no randomness in it, right? If you start at this point on the curve, this is the gradient. Go down there. Every time you run it, it'll be exactly the same. That's not the case with stochastic gradient descent. Okay, but it happens to be really, really good for these deep neural networks and training them. So who designs the reward signal? You do. And it's easy to design it wrong. One thing you could, I'm keep looking in Jacob's direction like he's going to save me here with cool examples. But one thing you could say is hey, I don't want the robot to use much energy when it walks. So I'll make my reward function energy usage or negative energy usage, because energy usage is bad, so we want it to be negative. So the more you use, the worse the reward, right? What would the robot do? Not move, turn off, basically. It would just shut off the motors, right? So be careful what you wish for, right? With reinforcement learning, but it's incredible. There's people use reinforcement learning for control of like fusion power plants in simulation, not in real life, to my knowledge. I don't think. I'm not sure. So anyway, that's the third major paradigm. Question. So what's the question? Can it be a function of multiple reward signals? So yes, in the sense that you could add the two reward signals together. But at the end of the day, it's got to be one reward signal. Then it's like, well, how much do I care about one versus the other? So if you want, the answer is yes. If you want to have multiple parts of rewards matter more or less, yes, you can add them together, multiply them by a constant. If that constant is huge, it matters a lot. If it's tiny, it doesn't matter quite so much, right? Who gets to decide what those little weighting factors are? You do. And if you have a lot of things you care about, you might be turning lots of little knobs to get it right. So it can become a real art at some point. Yes? So what do you mean by dynamic words specifically? So the question is, will we cover in this class methods of dynamically updating the reward through the training process? We won't cover that directly. That's an advanced topic. But I will say, if for your project, you say, I'm going to take this reinforcement learning algorithm and I'm going to investigate dynamic reward. And I want to see what I find. That's a wonderful project. Yeah, but we wouldn't cover it explicitly in this class. See, reinforcement learning is so much fun. Everyone has all the questions about it. Okay. But the key element is that you're interacting with the environment, right? You can't, so you, like, even if that environment is a computer simulation of a robot, okay? You have to interact with the thing that you hope to affect with the task. Whether it's saying, did I do a good job? Do I do a bad job? And you ask the person, they tell you yes or no. Then you're a part of the environment by answering that question. Okay? That's the key. With supervised learning, here's all my pile of data. Go at it. Go ham, optimize my model, come up with something. It never has to go and seek out more data necessarily from the world. This one you do. Okay? And as you can imagine, people have gotten really creative as different ways to combine these things. Okay? So one thing, and again, I'm sorry, I'm wearing the robot shirt, so I'll give you the robot examples on occasion, right? What is kind of common these days is while reinforcement learning can give you a good result, it can also take you a very, very long time, or the model gets stuck in all kinds of local minima when you're doing gradient descent, and it's not good. So sometimes people say, hey, if I want a walking robot, why don't I first tell it to walk like actual human data of humans walking around? What kind of learning would that be? Supervised. Why would that be? I guess okay, the answer is supervised, right? Because you're saying, I want you to specifically mimic this motion. You could technically turn it into a reinforcement learning problem, theoretically, whatever, but you want to make sure that it matches as closely as possible to labeled data. At this point in time, this is the angle of my arm. At this point in time, this is the angle of my leg. Right? So throughout this motion, I want you to make these motions, or these are what I want you to do, okay? Very specific. I want you to match that labeled data. But then after that, you say, okay, here is my controller. Maybe now I want to use reinforcement learning to make it better. And my reward signal is like going fast, not using a lot of energy, right? So you start at the beginning with supervised learning, and you switch over to reinforcement learning, right? That the people do all kinds of cool combinations like that. That's a very specific combination. Okay. All right, reinforcement learning. All right, further. So those are the three, I would consider them the three mains, okay? Then there are a couple of others. There's what we call self-supervised, where the idea is that you have unlabeled data, but you want to make some kind of classifier out of it, maybe. So you could use unsupervised learning to make some labels, and then use those labels to do some learning. This is the highest high level of how self-supervised works, okay? So it's sort of a combination of those kinds of methods where you use elements of unsupervised learning to learn labels, and then use supervised learning to classify. Now, this is a very oversimplified explanation, but I just want to show you that if I tell you there are three types of machine learning paradigms, there's some people who will say, nah, no, there are two. Or three, you're oversimplifying. There's actually five, or there's actually a lot more. But the ones I see listed the most as additional to the three are self-supervised, and this one is cool, semi-supervised. Okay. I'm just going to motivate this with a little graph first, a little graphic. Let's say you have a bunch of data. Here's all this unlabeled data. Okay? And that would be a unsupervised problem, right? All this unlabeled data. Let's say you have some labels. I'm going to put a little red X here, red X here, red X here. Little blue X, blue X, blue X. Those are labeled data points. Well, now you have a lot more information, right? You can look at this and be like, oh, not only does this cluster well together, there's also these three labeled data points that are the same in that area. So you can use a combination of labeled data, those colored X's, with the unlabeled data, those little dots, to help inform these categories, right? And that might be helpful because sometimes labeling data is somebody's job. In fact, it often is some person's job to label data. Who told the algorithm that that thing is a cat? Some undergrad in a lab at home. Cat, dog, right? That takes a lot of time. So maybe you don't have time to label all that data. Second. You don't have time to label all that data, but maybe you can label some of it. So that becomes a lot more scalable when you have giant, giant data sets. You can't label everything, but you can label some things. So it uses a combination of labeled and unlabeled data. Saw a question over there in the corner. I consider it a category of its own. Because it doesn't really fit in either of those two categories in a clean way. Not unsupervised, because you get data back. You get something and say, okay, here are my inputs. Oh, thanks for that data. That piece of data was a reward function. But we're not trying to predict the reward function per se. That is part of some of the methods. That's the, I'm assuming that's the value function part of the, anyway, I'm sorry. I'm getting ahead of myself. I'm mostly looking for your nods because you're the one who does this every day, right? But it's not, but if your job was to predict what is the reward for this controller, then it would be supervised. But that's not what we want. We want to maximize that reward. So it's different. So it's a completely different category, at least in my book. Yes? You could make it, okay, in the broadest sense, in the way I've phrased semi-supervised here, you could argue that. This is a very oversimplified version of what semi-supervised is, because I would say, like here, it's using labeled data to guide your classification of all this other stuff, or what to do. That's what semi-supervised is doing. Whereas reinforcement learning, it's not like, oh, some of the data is labeled and some of it isn't. It's you send in a model, you get back a number for everything you do. That's my thought. What's your thought? Hmm? 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 Doesn't need to be, right? Doesn't need to be. Fascinating. That's lovely. Let's talk after class. Thank you. Okay. For the purposes of this class, I wouldn't argue with you, but I'd say the top three that I would talk about are supervised, unsupervised, reinforcement learning. Okay. Interesting. So, all right. So those are our three types. So when you're thinking about your projects, and 3 types plus some extras, right? If you're thinking about your project, think about what you want to do. What data do you have available? Maybe you have a whole bunch of unlabeled data, and you're like, okay, how much of this do I have to label to make it a supervised learning problem? Okay. If you're thinking this might be a reinforcement learning problem, well, from what environment are you getting your data? Okay. All right. Any questions about that? No. None. Nifty. Okay. So let's go forward. Let's jump to, what are we doing in terms of time? We got 25 minutes left? Okay. So here's a big question. What's doing the learning? Okay. This goes back to Natalie's question. How does it learn? All this learning is, I feel like it has this, people who have not been exposed to it before, it kind of has this magical context because we associate it with our own brains, which are very complicated, okay? But the learning process is just, learning is just the process of finding the parameters of your model, okay? Is the process of finding the parameters of your machine learning model. It sounds a lot less magical when you say that, right? I mean, one way, yes, question. Oh, thank you. Thank you so much. Thank you. That's why we have, yeah, my producer over here. Thank you. I apologize. Thank you for that. Let's keep that zoomed out. Right? Sounds a lot less magical when you say it like that. I mean, who gets to, you could, at the end of the day, just magically pick a bunch of parameters for your model. I mean, what was the model we were talking about before? Linear regression, right? Y equals mx plus b. What were your parameters for that? M and B. So if you say just put your thumb in the wind, picked an M and a B, oh great, you just machine learned, right? Sounds a lot less magical, right? Or you could use gradient descent to minimize a cost function. And as gradient descent is moving around M and B, adjusting it little by little by little by little, what is it doing? It's learning, okay? Well, let's say it's more complicated than M and B. There's more parameters, right? The process of getting those parameters, that's learning, right? And so I should specifically say this is for what we call parametric learning, okay? This is for parametric learning. That's for parametric learning, and that's most of the learning you will do in this class, and a lot of learning that people do in general, where basically you have a parameter, and you want to come up with a better parameter, right? What could non-parametric learning look like? So a non-parametric learning, instead of having just a parameter that you update like this, where you get more data, so you get a bunch of data. Let's say you get more data, and you just update your M and your B. That's parametric learning. What if instead, I'll put this off inside in the blue, that you just have some term for your first data point that adds to your function. Then you get a second data point. You add another term. Then you add another and another and another. For all your data points. You're not changing any parameters. You're just adding stuff. You're adding new terms. Maybe you're adjusting the other terms as you go along, maybe not. Okay? But that would be non-parametric. An example will be something called a Gaussian process. Regression, or a GPR. So if you don't have a lot of data points, it actually might be a pretty good idea to use non-parametric methods like that. If you have a ton of data points, maybe less so. A little careful. Okay? But most of what we're talking about is parametric learning. So when I say learning is the process of finding parameters for your machine learning model, that's for parametric learning. Okay? So, but by and large, finding M and B. What if you had a lot more parameters? Still the same thing. You got to find them. The process of finding them is learning. Okay? So that means that that learning process might not look like this iterative process where you're guessing and checking and trying new things like we often think about learning to be. Okay? Okay? Imagine you had a magic equation that you could plug in your data, and then you churn through that equation and out pops M and B. That's learning, right? Okay? And believe it or not, such a thing exists for linear models. Okay? So. Okay. Let's see how much time we only have 20 minutes. We have to do something else here. Okay, we'll save that for another time. So we'll say for linear models, where your y prediction is equal to your decision vector W transpose times X and your cost function is quadratic, there is a non-iterative solution to finding the best parameters W. Okay. And I would just refer you to chapter 5 in the Goodfellow text. And if you wonder where, if you're having a hard time finding the Goodfellow text, if you haven't been following along already, there's a link on the Canvas page, on the front page, okay, to the official Goodfellow textbook page. It's page 107. Okay. So from a linear algebra standpoint, this W transpose X All that means is that if W is a list of all your decisions in a vector W1, W2, up through Wn, and X is some prediction of some set of data, X1, X2, up through Xn. And you could use this for any kind of polynomial fit, by the way, in case you're curious. Okay? What W transpose turns this into a row vector, and then this is X, W, transpose X. This would be an N by, sorry, 1 by N. I heard someone say, they were right. That's a 1 by N. That's an N by 1. The rules of matrix multiplication says that in order to multiply two matrices together, these have to be the same. They are. And the result is a 1 by 1. That's your number. That's your prediction. Okay? And the result of this matrix multiplication, it looks like W1, X1 plus W2, X2 plus Wn, Xn. So instead of writing this, people just write W transpose X. That's easier. Okay? So learning may not require gradient descent. This non-iterative method. Technically, there are iterations happening in a matrix multiplication, blah, blah, blah. I'm sure someone would love to argue with me. It's okay. All right. Take a look. All right. So, however, many of your problems that are coming up absolutely will require you using gradient descent. You don't need it for linear regression. You don't need it for polynomial regression. Okay? But for nonlinear models, they require iterative methods to find the best W, e.g. gradient descent, or its variance, which we'll talk a little bit more about later. Okay. What is such a nonlinear model? Okay, an example. Okay, talk about this a little more later, but this is a bit of a preview. It's an artificial. Sorry. Artificial neural network. Okay. This particular one, or the idea of an artificial neural network is that it'll consist of what we'll call neurons. Okay. Often draw them in a little circle. We'll have some kind of input X. I'll call some output Y. And often you'll see them drawn with a little whoop in there. Sorry, I'll give a little, make it a little cleaner. Something like that. Okay. That little shape we call an activation function. Okay. And that could be a whole bunch of different things. We mentioned a few of these before. We talked about the tan-H's, the tanches, the hyperbolic tangents. Tan-H, something called a ReLU, a rectified linear unit. It just looks like a little elbow. Tan-H, which looks like an S. Sigmoids that look like an S. There are lots of things you can put in there, okay, for depending upon your application. But one thing that they're not is they're not linear. Yes, the one of them looks like two lines, but it doesn't count. It's got to be one line to be linear. Okay? These are nonlinear. Okay. All right. That's a neuron. And the idea with a neural network is that you don't have just one neuron in your neural network. You might have many, where the output of this neuron goes into another neuron, and then another neuron. Or, what is extremely common and incredibly powerful is that you might have layers of neurons, okay, which are connected. Every one to every other one is called fully connected. Oh no, what did I just do? All my hard work. Gone. Look at me connecting every neuron to every other neuron. Look at that. Okay. Connect them all up like that. And so the equation for what you have some input, x, and some output, y, will be the number goes in, it gets tanh-H'd or ReLU'd, and then it comes out, and that number gets spit out to all those other neurons. Multiply by some number, w, a weight. If it's important, it'll have a big number. If it's not important, not a big number. Okay? But this neuron will not only have this coming out, multiply by some w, 1, it'll also have this coming out, multiply by some w, 2. And same for all these other ones. They go in, they go in, they go in, and they're all added together. And then they go into that neuron, and then they get tanh-H'd again, and then comes an output. Yes? If it's a ReLU, kind of. If it's a tanh-H, absolutely not. Kind of. I feel bad answering that question. I haven't thought it through. So I'm going to say kind of. Yeah. It's actually, well, there's definitely an if-else component, because if you're in this range of it, it's 0, and this range of it is some other value, right? So there's definitely if-elses in a ReLU. Okay? But no need in a tanh-H. That's just a smooth function. Yes? No. There's nothing stopping. You can do whatever you want, dude. I don't know how common that is, though. When I read papers on these methods, like, it's just like, we do a layer. So this whole group right here, it's called a layer. That's right. When your students ask a question that requires more lecture, you know you have good students, so that's good. So it's a layer, right? The layer of a neural network. Here's another layer. Okay? This particular thing is going to be called a multi-layer perceptron. How are we doing on time? I'm at 9 minutes. So this particular thing is called an MLP, or a multi-layer perceptron. Now, we'll cover this again, don't you worry. The point is, you have all these nonlinear functions, which are then all multiplied. The outputs are multiplied by some w. Then they're added together. And then that result is put inside of another nonlinear function. And then the output gets all added together out at the end here. So you're not using linear algebra to solve that directly, just like we did with the linear models. We have to do something else. We have to do something like gradient descent. But my friends, I want you to think in your head what this function might look like. Are you brave enough to do that for a moment? Just in your head. You have tanh-H's within tanh-H's multiplied by other tanh-H's, or ReLUs added to other ReLUs and tanh-H's. And I say, that's fantastic. Open your eyes. Take the derivative of that with respect to w. When we did that in lecture on Thursday, that was easy, right? We just had a function, it was like it's a quadratic. We took a derivative with respect to w, boom. In our sleep, we could solve that derivative. But those derivatives are super important. So how do we get them? Okay. So finding derivatives with respect to model parameters is paramount to using gradient descent. Okay. You don't want to take that by hand. You don't want to take it by hand. Not by yourself, for sure. But there are a couple ways that you might try it. And one of which is now the standard for how you come up with gradients for these artificial neural networks. Okay? I mean, one way is using computer algebra that take exact, what we sometimes call symbolic derivatives. So who here has a calculator that can take symbolic derivatives for them? No? You don't know how, but it can. You do. You have one. What model calculator is that off the top of your head? CICX2 Inspire. I just realizing how old I am. I have no idea what that is. When I was a baby, yes, in the crib with my TI-83 calculator, okay, it did not have it did not have computer algebra packages. And what do I mean? So like normal calculator, 1 + 1 = 2, 2 × 2 = 4, those things, right? But the TI-89 had computer algebra in it. I could say, what's the derivative of x squared with respect to x? And it would tell me 2x. Oh, glory, right? I can do that with basically any function, and it'll tell me the derivative. The computer will do it for us, right? And guess what? That's built into MATLAB. You all use MATLAB, right? Oh, symbolic toolbox is built in, baby. It's great. But I'll tell you, not a magic answer to this problem. Those neural networks get so complicated, you know, it's not actually magic. It actually takes a very long time, and that derivative can become huge, huge for a neural network. Maybe it's not a good idea. Okay? There's other methods. One called finite differencing. It approximates. I don't know why I put that in scare quotes. It actually does approximate. Approximates a derivative by perturbing the decision and measuring the slope. Okay. Nice thing about that, so imagine that you have some x, some w, and some function of w, and you put in a w. This is our current guess of w. We'll call it w0, right? And then we try a little tiny little change of delta w, and it comes out right there. Well, we can say, oh, rise over run, that's the slope, voila, we got the gradient. And we can do that for every single decision. And it does not matter very much how complicated that equation is. You just got to plug it in, get the number out, plug in another number, get another one. Problem is, when you have tons of w's, that starts to slow down, right? That means you have to keep checking this function over and over and over again with different w's just to get your derivative, okay? So it does not scale well with many decisions. W. What if you had a billion decisions? Just to get a gradient, you have to check a billion of them. All right? This leads us to a whole other category. It's not fully symbolic, but it's not fully approximate. It's not approximate either. Okay? All right? And what you'll often hear something, the phrase you're going to hear is called back propagation. Or an algorithmic differentiation. Or an automatic differentiation, or auto diff. Okay? These are different, they're all very related, okay? But the idea is that when you are taking the derivative of a function where you have functions within functions and within functions within functions, you took the derivative of, for instance, ddw of sine of w squared, what do you have to do? You have to take the derivative of the outside, cosine of w squared, then multiply it by the derivative of the inside. Okay? Right? That's the chain rule. Okay? And you will see, if you do a whole bunch of derivatives, all in a big neural network, you'll see lots of the same terms popping up over and over and over again, right? So instead of computing them over and over again, compute them once and remember them and have a smart way putting them in the right place with the chain rule. Okay? So back propagation is a huge step forward in how we compute derivatives for neural networks. We are out of time. Okay? On Thursday, see you on the Zoom session. Thank you for coming by.